Good morning all. Today I want to play around with this thing. It's a module containing 6 supercapacitors. Each one is 2.7 volts, 120 farads. Now because they're wired in a series string, the total capacitance of this thing is only 20 farads. It's 120 divided by 6. So what I want to do is I want to charge this up. Well, first perhaps I'll just see if it's got any charge in it. Charge it up to the maximum voltage, which will be 6 times 2.7 volts. Discharge it with probably a little light bulb, which I can attach between these 2 points here. And also I want to check out the operation of these little protection circuits. These circuits are designed to stop the capacitors going over 2.7 volts. Now, of course, they're only going to be able to do that by passing a current. When this transistor switches on, it'll pass a current from one side of the capacitor to the other, and so it'll only be able to protect the capacitor if no more than that current is flowing in. If you push a lot of current into this, then you could take these over the 2.7 volts. But let's have a look at all those things: charging it up, discharging it, checking out these protection circuits, and just seeing what we can do with it. So this device I first looked at in my postbag video, Julian's postbag number 68. And I'll place a link to that video in the description. Let's also have a look at this on eBay. This is it, farad capacitor, 2.7 volt, 120 farad, 6 pieces, with a protection board module, $17.28, a bit of shipping on that, so about $18 this is, and it came from Bywee City. And I'll link to this eBay listing in the description below. Okay, let's start by seeing if there's any charge in this module. So this is the negative end, so I'll put the, make sure I'm not on current. No, I'm not on current. I'll put the negative probe there. Oh, there's absolutely nothing, is there? Oh no, there's 3 volts. Okay, 3.36 volts. If I take that off, I'm getting some millivolt reading. Okay, so there's a little bit of charge on there, but given that this thing can go up to 16.2 volts, it's not very well charged. Right, let's see if that's enough charge to, or enough voltage at least, to light this small light bulb. This is 12 volts, 0.1 amps, I think, so it's about 1 watt. And yeah, that's just about lit up. Now what I might do is attach this permanently to the module so that this can discharge the module, and then I can start thinking about charging it using some sort of power supply. Right, I've soldered this little bulb to these contacts here, so that's going to be gradually discharging the module. It does seem to be getting dimmer and dimmer, so I expect that'll go out pretty soon. Okay, so now I'm going to rig up a power supply so that I can charge this unit up. Okay, here's my setup. I've got the capacitor module here with the light bulb there. That's now gone off, so the charge on the capacitor has dropped down to probably almost nothing. I've got my power supply here. That's set to 12 volts, and I've set it to 200 milliamps because I know that lamp will draw about 100 milliamps. So if I put 200 milliamps into the capacitors and 100 milliamps flowing out, then there will be a net charge or current flowing into the capacitors of 100 milliamps. And it should charge up and the voltage should rise up, and we'll see that on the light bulb. So 12 volts. It won't be 12 volts, of course, to start with, but let's switch that on. Okay, so what have we got? We've got current of 200 milliamps, and the voltage is pretty low at the moment, 1.8. Now that's going quite slowly, so let's go back to current and raise that up. Let's go up to, say, 400 milliamps. I didn't realize it would be this slow. Okay, can I save that? Yeah, I can, but I'll have to switch it back on again. Okay, so the voltage is coming up a bit quicker now. 2.4. Incidentally, I've put a diode here. You can probably see that if I put my torch on. That's just a 1N4005, I think it is, because some power supplies say if you're charging a battery, put a diode in the circuit, because you don't want, when you switch the power supply off for the battery, and that's what this is effectively, to pass a current back into the power supply. Now I don't know whether this one would be affected by that, but I've put the diode in any case, and that's still going up quite slowly, so maybe I'll raise the current a bit more. Right, now I've got a current of 500 milliamps, half an amp, so let's switch that on again, and the voltage is at 3.7, so I'll let that climb up steadily. Now I don't want to go much beyond 500 milliamps. This is a net charging current, of course, of 400 milliamps because the bulb is taking about 100 milliamps. It won't at the moment because it's quite dim, but as that brightens up it will draw that sort of current. The voltage is climbing up, so we're getting a net current into the capacitors. The charge is building up on those capacitors, so I'll just leave it going for a while. So the supercapacitor module is now at just over 8 volts. We're still drawing 500 milliamps, and the voltage is still climbing. Now, because I've only got 12 volts coming into this module, actually it's a little bit more, I'm just passing it through this boost converter, but it's switched off, so it's just in pass-through. There's actually 13 volts here going through, a little bit of a diode drop there. So I can probably put up to about 12 volts on this module. Now when I want to go higher, up to the maximum 16.2 that this will take, I'll just switch the booster on, so I've got a bit more voltage on the input of my buck power supply. But let's let that get right up to 12 volts to start with. Okay, so the supercapacitor module is now at 11.88 volts. The current's dropped right off because we're nearly at voltage parity. So we're not charging at the full 500 milliamps. We're only a little bit above what the bulb's taking, so actually it's not really going to creep up very much more now. Right, if I want to take the voltage on this capacitor higher, I'm going to have to switch the booster on, so let's do that. That's going to raise up to about 20 volts. That's on the input of this now, so I can raise the voltage of this up. Let's take this to 16, because the capacitor bank can go to 16.2. So let's take that to 16.0. So that's 16 volts, half an amp. Okay, let's switch on and push this thing up a bit higher, close to its maximum voltage of 16.2. So I'll just leave that running for a bit. What current are we drawing? 500 milliamps again, and wait till we get nearer 16 volts. Okay, so the power supply has reached 16 volts. The current is dropping, which is interesting because the voltage is not changing. So there's some sort of absorption going on, I think. Not quite sure what that is. But anyway, 16 volts. Now this has a maximum of 16.2 because each of the capacitors is a maximum 2.7 volts. But it doesn't necessarily mean that they're all going to reach that voltage at the same time. So it's quite possible that one or more of these protection circuits has already kicked in and is holding the voltage on a particular capacitor down to prevent it going over the 2.7, but we don't know that because we can't see what's going on that circuit. So let's have a little bit of a closer look at these protection circuits. So each capacitor on the module has a little circuit that stops the voltage on that capacitor going over 2.7 volts. What we've got here is a little device called a voltage detector. Now in my postbag video, a couple of commenters, very helpfully, thank you very much, identified this component, so I'll get the datasheet for that. But what this does is at exactly 2.7 volts, this unit switches on and it will turn on this device, which I think is probably a MOSFET, and that will put these two resistors. Now I probably wrongly called these 100 ohm. I think they're more likely to be 10 ohm, 1, 0 and 10 to the 0 multiplier. So 10 ohms, 2 in parallel, so that's probably 5 ohms. Now if we've got 2.7 volts there, let's call it 2.5, 5 ohms, then we've got half an amp of current will be flowing when that MOSFET is on and discharging that particular capacitor. Now this device here, this voltage detector, has a little bit of hysteresis, so the voltage will need to drop down by a small amount before this thing switches back off, the MOSFET turns off, and the protection circuit is, well, these resistors are disconnected from the capacitor. But what I wanted to do was somehow see these circuits switching in. So what I want to do is put some LEDs on these circuits, And initially it occurred to me that I could put an LED with a series resistor on the output of this voltage detector device, because it's got quite a high current output drive. But actually I don't think I need to do that. I've come to the conclusion that I can probably put a diode directly across these resistors. And that's because the only time that these resistors are going to have a voltage across them is when this MOSFET is turned on and is essentially stringing the resistors across the capacitor, so they'll have 2.7 volts across them. That voltage will then drop down slowly, this device will turn off, and then these resistors will have no volts across them because this connection here, the drain of the MOSFET, will be just floating. And so if I strap an LED across these resistors, it'll either have 2.7 volts on it or no volts. Now 2.7 volts on a blue LED is not enough for it to draw a huge current, so I can put that across there without a series resistor. What I just need to do is check that 2.7 volts on a blue LED is going to be bright enough for us to see it. So let's do that now. So I've put a blue LED into the output of this power supply. I've set it to limit at 2.7 volts and about 30 milliamps. That should be more than enough for that. It's not going to draw anything like 30 milliamps at 2.7 volts. So let's switch that on. And the LED comes on and it's perfectly bright enough to see at just 2.7 volts. What current is it drawing? Well, almost nothing, about 2 milliamps. But that's fine, so that's not going to stress the circuit on the capacitor board. So I can solder this LED straight across those resistors, and when it's got 2.7 volts flowing through it, it will draw a couple of milliamps, but it's easily bright enough to see. So we can see the protection circuits kick in. Good. Okay, so I've soldered my blue LED directly across the resistor on just randomly one of these protection circuits. I will eventually put an LED on each one, but I just want to see if I can see that LED come on when that protection circuit kicks in. Now I've no way of knowing whether this is going to be the first one to kick in or the last one, but if I try and take the voltage of this bank high enough, then they should all come on eventually. So let's just see if that does come on. Right, so I've set this now to 17 volts, which is above the voltage that this thing can tolerate, half an amp, so that I don't overwhelm these protection circuits. So let's turn this booster on to get 20 volts on there, so that I can now turn this on at 17 volts. And it's 9 at the moment, so I'm going to have to wait a little while for this to creep up, approach the 16.2 volt maximum, and hope that one of these LEDs comes on, or that LED comes on. So I'll come back when this is getting close to 16 volts. Right, the voltage is 15.8 volts and climbing the last little bit. So now I'm expecting the protection circuits to kick in as we approach 16.2. I don't know, as I say, whether this capacitor is a high capacity one, in which case it'll be last to trigger its protection, or a low capacity one, in which case it will trigger first. But we should see something fairly soon. I'm over the nominal voltage of the pack. I'm not quite sure why I'm not seeing that circuit kick in. 16.4. Not sure how high I dare go. Right, I'm having trouble getting these LEDs to come on to show that the protection circuits are kicking in. One thing I didn't factor in was the volt drop across this diode. So the reading on my power supply is going to be high. Let's switch that on. That's 15.5, and I've got actually 14.7 on the capacitor module. So in fact, I've got about a 0.8 volt drop across this diode, a bit more than the normal 0.6. 15.7, well, we're just hitting 15 there, and that's 15.8. So really I'm supposed to be watching this, because that's the actual measurement of the voltage on the capacitor module. Wait for this to get to 16.2, and then these protection circuits should start kicking in. So I'm now standing with my face behind the camera, so that if this thing blows, it doesn't blow into my face. 16.8 on the power supply, but only 16.0 on the DVM. When we get close to 16.2, those protection circuits should kick in. Are they going to do it? Is this capacitor bank so well balanced that they all kick in together? 16 point, almost 17 volts on the power supply now. A protection circuit has come in. 16.23, 24. Will the other protection circuits kick in as the capacitor bank voltage rises ever further? Yep, they're all starting to kick in now. And the module voltage is now starting to fall, presumably because there's sufficient voltage across these capacitors. Well, there's sufficient current flowing through these discharge resistors, but I'd be surprised if it could. Actually, yes, it will overwhelm this, because I've actually turned this down. I suppose I should show what this is at. This is at 300 milliamps. So it's more than the bulb. So I've got a net current flowing into the module. That voltage is creeping up again. This seemed to be the first one to trigger, that top right-hand one. There is hysteresis on these voltage detector chips. We'll have a look at the datasheet soon. That seems to be going quite high now, without those chips kicking in. Now we've got this one kicked in. Actually, of course, yes, because these cells which have had this bit of discharge applied will now have switched round, so they'll be the lower voltage ones. So the other circuit should now kick in. Oh, it's a random light show. This is really good. But that should be stable, because I haven't got enough current to overwhelm the discharge circuits. I have got enough current to overwhelm the bulb. So we should just now get a random light show of protection circuits kicking in. Those capacitors will then go down in voltage, and it's all protected. It's all rather good. But we're very near the upper limit of the voltage on these capacitors, because these voltage detector chips are set to 2.7 volts. So it's letting the capacitors go absolutely to their maximum voltage, and by the look of this, somewhat beyond. Because we shouldn't really be more than 16.2. Now, have all those protection circuits come on at some point? Now 16.5, that does seem quite high. Getting ready to get near the off button. 16.6. Off. So I'm going to do another run. Am I feeling a bit braver this time? And it's already way above the nominal maximum voltage that the module is supposed to support, 16.5. And these lights aren't coming on. Just not sure why they're not now kicking in. There's one. They're at a very high voltage now. 2, so the top 2 work. Bottom left. I'm not sure I've seen all 6 of them come on yet. This is all a bit strange. Right, the other 3 have come on now, so I'm pretty certain I've seen them all come on. Got a feeling this is a bit near its own limit, because I think I saw that change from constant voltage to constant current. It looks like all 6 protection circuits do work, and when they've pulled enough voltage out of the capacitor, they switch back off again, and then presumably the other 3 will come on. Fascinating stuff. I'm just sitting here watching it, and I had I had 5 of the 6 on just then, and now they're all going back off again. I think the only one of the 6 that didn't light on that cycle was bottom left, so that one should now be getting quite high, and I would imagine bottom left is the next one we'll see light up. Yes, there it goes. Well, this is great fun! But it does make me just a little bit nervous that the voltage on the whole pack is seemingly way above what it should be, 16.2. It should never go above 16.2 because if the capacitors are out of balance, which they are, one will always be higher than the other 5. And so this should be triggering way before this sort of voltage. I don't know what the tolerance is on these capacitors, how much over voltage beyond the 2.7 that they're meant to be able to tolerate you're allowed to go. I suppose I could look that up. But yes, all 6 of those protection circuits are certainly working. It's just that the voltage is all a bit high. Right, I've just managed to get all 6 lights to come on by raising the current on this power supply slightly so that it's only just offset by these balance circuits. So I've got 400 milliamps coming in here, 100 going out with the bulb. That should be a net of 300 milliamps going in. The balancing circuits are capable of discharging about 500 milliamps each. But certainly the more current I put in from the power supply, the harder the discharge circuits have to work to keep the capacitor voltages down. Now I could, if I raised this current up beyond 500 milliamps, or at least beyond 500 milliamps plus the bulb current, overwhelm these discharge circuits and they would never be able to switch off, and in fact the voltage would just keep creeping up. I don't feel like doing that at this sort of voltage. I'm over the 2.7 of each capacitor anyway. I just don't feel comfortable letting this get up much, or approaching 17 volts. That doesn't feel too good. Let's just see if we can get all these lights to come on at the same time again. 5 circuits all switched on. Is that top left one going to come on as well? The voltage is actually dropping back on the capacitor bank, so maybe they'll start going off instead. Yes, they are. I could watch this all day. Now these capacitors are all a bit warm. Should capacitors be warm? I'm not completely sure about that. Anyway, I'm not going to move on to sketching out. I'll go and get my pad. I'm going to sketch out the protection circuit so that we can see how it works. So each protection circuit consists of this small SOT23 device, which is marked C73X. And as I say, this device has now been identified. This device down here, which looks like it says I13 and then that logo, but I can't identify that logo, but I think it's a MOSFET because the output of the voltage detector, this C73X, is taken directly to the gate pin. Now if this were a Darlington or a bipolar transistor, you'd expect a current limiting resistor in the baseline, so I'm pretty sure that's a MOSFET, but it does have a very low gate threshold because there is no voltage greater than 2.7 in this circuit, well, possibly slightly greater. The MOSFET source is tied to capacitor negative. When it turns on, it just takes these 2 resistors, which I now think are 10 ohms each, so 5 ohms in parallel, and just simply pulls them down from the capacitor positive to capacitor negative, and therefore allows a current to flow to discharge the capacitor. So let's draw that on my paper pad. So we have the capacitor. I'll draw that quite big. Positive at the top, and strapped across that is the C73 device, C73X, and it simply measures the voltage on I think this is VDD and ground, and it has an output which goes high, presumably, when this voltage exceeds the threshold. Now this device has a threshold of 2.7 volts. That appears to be connected directly into the gate of a MOSFET. Can't quite remember how to draw an N-channel MOSFET. The drain has these two resistors. Let's put them here. Draw them as one resistor. That's in the drain, and the source is tied to ground. I think the arrow goes something like that. And then this goes to VCC, so that when this MOSFET turns on, it simply pulls this end of the resistor down to ground, and I think that's 5 ohms, and therefore starts to discharge the capacitor. That, I think, is the circuit. Now this is the C73X, and this MOSFET is called an I13, I think. Now I've drawn another one here, laid out slightly differently so I can put my LED that I've added on. This is a blue LED, and of course the whole system voltage, if you call this a system, here has a maximum of 2.7 volts. So that LED can never get very bright, so I don't need a current limiting resistor. The MOSFET simply turns on and the LED is strapped directly across the capacitor. Now of course there are 6 of these circuits, all in a series string, so that you've got your 6 capacitors in series. That reduces the overall capacitance, of course, but raises the total energy holding amount, because you've got 6 times the physical volume of storage. I'm not going to draw all 6 circuits, but what I want to do now is look at the datasheet for this C73X voltage detector chip, because this is the thing that's measuring the 2.7 volts across the capacitor and switching on its output to turn on the MOSFET. So this is the datasheet for that device that's marked C73X. It's made by Torex. It's an XC61C series low voltage detector. That's any device going from 0.8 to 1.5. So this one is a standard voltage detector, somewhere between 1.6 volts and 6 volts. This one happens to be 2.7 volts. The XC61C series are highly precise low power consumption voltage detectors manufactured using CMOS and laser trimming technologies. Detect voltage is extremely accurate with minimal temperature drift. Both CMOS and N-channel open drain output configurations are available. Now the one that's being used is a CMOS. So the block diagram of the device in this circuit is this one with the complementary MOS output, so that this Vout can be pulled up to Vin or pulled down to VSS. The other one just has a pull down N-channel internal MOSFET, so it's open drain, but that's not the one that's in this circuit. And we know that from these markings. These are the markings of the SOT23 device. So it's a C, that means it's a CMOS with a 2-point-something volt switching threshold. The 7 will be here, so it's a 2.7 volt switching threshold. And what was the other thing? Oh, that's the other device. That's the bigger one, the TO92. Let me just scroll that a bit. And so the third mark, the X on the end, no, the third mark is no time delay. The X on the end is this 4th one, and that's just simply a production lot number. So C73 simply means CMOS 2.7 volt threshold. So in the electrical characteristics, the detect voltage VDF is typically VDF. It can be as low as 0.98 of that, or as high as 1.02 times that. But there is also hysteresis, which is why these things don't flicker rapidly. They switch on, hold for a while, and then switch off. So the hysteresis range is typically times 0.05 times VDF. So it's 0.05 times 2.7 volts. And that is 0.135 of a volt. So that's the hysteresis. It can... Now, I don't know whether the hysteresis is either side of 2.7. I would have thought that 2.7 is the switching point, and the hysteresis is all below that, because you don't really want to go over your trigger voltage. But maybe the hysteresis is either side of the detect voltage. I can't quite work that out at the moment. Operating voltage of the standard voltage device is 1.6 to 6. This one will trigger at 2.7. Now output current on the standard device at V in of between 2 and 3 is only a few milliamps, so it can't switch that much current, but of course it's enough to switch the gate of a MOSFET. So that's how these circuits work, but I must admit, I think I'd have been happier if they'd gone for something like a C5 3X, where the 5 was 2.5 volts, sacrificed a little bit of module capacity, but had this thing switch in the protection some way before the 2.7 volts. The fact that they've gone for a 2.7 volt threshold detector, which does appear to not actually kick in until it's quite a bit higher than that, well, that's by my findings from my DVM, is a little worrying. Now I'm just charging this thing back up because that bulb had discharged the unit. Now I just want to do some calculations. If this MOSFET is turned on, let's ignore its on resistance, it's probably quite small. We've got 5 ohms, 2.7 volts, so I equals V over R, that's 2.7 over 5, and that is 540 milliamps. Now what about the power dissipated in that resistor, or the pair of resistors in parallel? What's that? W equals I squared R? Yes, or well, V squared over R I suppose we could do. And that's approximately 1.5 watts being dissipated in these resistors. 1.5 watts in these tiny resistors. I would imagine they'd feel quite warm. I think I might put my hand on them in a moment. Right, so I'm now at the sort of voltage here minus the diode volt drop where these cell protection circuits are starting to come on again. What current am I driving this at? 400 milliamps. I've got 5 of them on. Oh no, they're all 6 on. Oh, one's gone off again. So it doesn't really seem to balance these capacitors as such. Because of the hysteresis in this chip, it seems that some hit their top and then are pulled down again. It never actually gets all 6 of these in balance. Not that there's any reason to balance this particularly. You just want to protect each capacitor from going over the top. Now, of course, if I put a current down through here of greater than this 540 milliamps, so I'd need probably 600 milliamps here minus 100 milliamps here would be about 500. I could overwhelm this discharge circuit. There'd be so much current flowing into the capacitors through here that these discharge circuits wouldn't be able to compete, and the capacitors would just keep going up in voltage, and I could destroy the module. So I certainly won't be doing that. So it does mean that you have to keep the charge current going into this module, minus any current coming out, to below this figure, which is the maximum that this resistor can pull out of each capacitor when these circuits are switched on. Oops, I touched the electronics with my graphite-tipped pencil then. Not a good idea. But yeah, that does seem to be working, but worryingly high voltages on that module. Can we get all 6 to come on? No. They're starting to go off. But yeah, great fun little module, even if it does get a bit warm. So I think that's probably about as far as I can go with this module. Not entirely sure what I'm going to use it for. I think it might be quite fun to try charging it from a solar panel, possibly. That's when we get some sun. Actually, it is quite sunny today. But that's probably the next thing I'll do. But I think for the moment, that kind of wraps this up. So, cheerio.